if this material have the sufficient thickness, so you could actually have this cascade process going on. You could have a photon with pair production to electron, and then they brainstorm loosely energy, and then radiate the photon. And if they have sufficient energy, then they just undergo this brainstorm and pair production process until the end that all the particles have low energy, cannot further interact with the material. So we call this is a shower process. Yeah. So we have a typical characteristic to define what is the radiation length. So if you go through some material depth and you lose the energy of 1 over exponential, then we call this material length called radiation length. Okay. So this is the EM part. Basically, it's electron and photon interaction with the material. And how about muon? Muon, and this for the this is the plot that how muon loses its energy as function of different velocity, beta, and also the if you translate to the momentum of the muon, and you can see the scale here. And in terms of the momentum range that we care about in Large Hadron Collider, most of the muon, they are produced within this range. Yeah. If you have a Z boson, 90 GeV equal to the 2 muon, their transverse momentum is usually 40 GeV. So with this kind of energy, that the muon usually behave like a minimum ionizing particle. So they will behave like how electron ionize the energy. Okay, but you also see if your muon have a relatively high energy, okay, then you can see that it loses energy quite substantially, and this is actually the case that muon could behave like an electron. It can brainstorm, radiate high energy photon out. Okay, so this is the how a muon typically interacts with the material. Then I would like to move on to the topic like how quark or the QCD object that interact with the material. So due to confinement, we know that there are no free quark or free gluon exists. So whenever you produce some gluon or quark, and they will go through a hadronization process, as I mentioned in the morning. And the way we describe in the hadron collider physics that we could have a particle level calculation. Okay, so for this part, you can apply your basic electricity rule and for how a particle branching out produce a shower of the gluon and the quark object. Then we move on to the hadron level, that how different quark they form hadron, either a meson or baryon, and then they arrive the detector. So all these process, these are QCD process, so they happen almost right away around the collision point. Then all these hadron just flies to a distance, reach your detector. So we have a detector called the hadron calorimeter. So based on the name, you know that it's a calorimeter which can measure the energy. And it's designed specifically for the detection of hadron. And this process actually, when you have a hadron particles reach the material, they have a strong interaction with your material. So it will undergo similar to the shell process we described earlier, but this is a strong interaction. Okay? So in this kind of hadronization sharding process, we also benchmark the interaction through some characteristic number. We call it interaction length. That is, what's the typical length, the material depth that when you lose the energy of 1 over exponential of the additional particles. So I show you a real picture about an accuracy event display. Again, this is an R5 view. This is a user angle. So here we show that you have 2 cluster of the object here, and you can see that they have a high density of charged particle deposit trajectory in the inner detector, in the tracker. Then the green is called EM calorimeter, and the red is the hadron calorimeter. So you can learn that this is a very good candidate for the either quark or Coulomb. What happens is that it produces a lot of charged particles, but it also has a mixture with some neutral particles. And not only that, it also deposits energy in the hadron calorimeter. Okay, so if this is a photon, instead of a quark or Coulomb object, you will basically deposit all your energy in the green calorimeter. You will not further go beyond that. And if it's not a mixture of the neutral particle, it's a pure charged particle, what you will have is that you should not deposit such a large cluster of energy in multiple cells in the calorimeter. Okay? So here, you can see that a flat plane here. So what happens is that this is the phi dimension of the calorimeter, and this is the RZ view. This is the beam moving direction. Okay, so we know that pseudo relativity is defined connect to the polar angle definition. So what we do is that we basically just this is the barrel picture. So if you open this barrel picture, make it flat, then you have the coordination of the phi versus eta along this direction. And the z-axis is just how much energy deposited in a particular phi eta coordinate. Okay? So I want to mention a particle Coulomb algorithm. This is advanced jet reconstruction technique has been adopted and used successfully in CMS. So what happens is that CMS has an algorithm which you can take into account how the response of charge track component of a jet and the neutral component of the jet in the calorimeter, and how to compensate one from the other and get the best distribution of the jet. So this kind of the combined usage of full detector information still need to be developed in Atlas. Yeah, so James did a very wonderful job here. Okay, so we mentioned a lot about all different things. But actually, when we experimentally trying to do experiment, we have to ask what kind of particle you have to detect. Because now we learn that for different objects, you need a different technique to detect them. And also, what's the property you care about? Their position, their lifetime, their quantum number, energy, or charge. And after all, we define all these, measure all these stable particles. But what we really care is that where they are really produced, what's the underlying physics behind that? Okay. So this is a brief summary about all those 5 major step particles and how they could be identified using different combination of the detector. Just give another review. If it is a photon, it has no charge, so it will not have the ionization of the molecule inside the tracker. So you have no trajectory, but it will initiate EM shower in an EM calorimeter. So you can see it based up here. And for example, the muon is basically the mineralizing particle all the way through all the detector. So this is a typical signature of muon. Except if your muon go beyond the 300 GeV, as I mentioned earlier, it could actually start behaving like a photon. It will also behave like so it will behave like an electron. Also have a brainstorm photon could be detected by the EM calorimeter. Right? So, and then finally there's an interesting object which is called the missing energy. So the idea is that you have neutrino could be produced in a detector, but neutrino has almost no interaction with your material. So what we do is that you can sum up all the energy that you measure, that all the other particles deposit in the detector, and you do a vector sum. So then eventually you will see that the energy of the whole event will bias toward one direction because of the energy momentum conservation in the transverse plane. Okay? Then we take this minus sign of all the sum, vector sum of all the other two-dimensional four vectors. Then we define it as the estimate of the neutrino. Okay, so as I mentioned that the reason why we eventually can only detect the step particle because we try to apply all knowledge of the dynamics and also the kinematics of particle physics. When you have some unstable particle produced, they will undergo a series of decay to all the final step particle. So what we do is that we identify those final step particle, and then we reconstruct their four vector, and we can look at a list of many collisions. If you have the new physics happen, for example, a resonance happen, you can see some resonance show up in your data. So let's summarize the basic particle detections. I want to highlight also the success of the Large Hadron Collider physics. It's not just the particle detection, but we also revolutionize the way we do the computing. And in particular, Taiwan actually also played a leading role here. We have a tier 1 center which contribute to the significant on the evaluation round 1 data analysis. Okay. All right. So that basically my introduction about detector. Then I will move on to the next topic, and the Cerner model. That what's the big deal in Large Hadron Collider? Okay. So actually, I could summarize in one slide. Basically, we did a lot of Cerner measurements. It's all consistent with Cerner predictions. Okay. So if you feel comfortable, we can probably stop here, ready for the dinner. So, but is that true? That how do I understand this plot? This plot is basically y-axis is the production cross section. The x-axis is all kinds of different channel predicted by Cerner model physics. So for each point here, we have the data measurement. For example, this data measurement including the central major value of the data and the data uncertainty. Okay, and then we overlap with a theory prediction. Okay, so you can see that. Let's take one example: top production. So top production, that basically the theory prediction and the data measurement, they are basically just right on our measurement consistent with the theory prediction. And not just the top physics. And if you look at you have a top with one additional photon radiation, yeah. And now the experiment still have a quite large uncertainty. But if you just look at central value, it's beautifully that just theory just predict the real situation very well. Yeah. So we continue to move on that if the high production channels that the CERN model could describe the real data very well, then how about the real process? Because the real process is the new process that we had never seen before. So they become a highlight that we try to see. Since we never see before, so there's a hope that when we really be able to measure it, we have a chance to see some discrepancy. So these are the channels that in Large Hadron Collider we still we are working hard trying to see how those channels looks like, and they have a chance to lead to some big surprise. Then how do we test the model? So we need the several components. Basically, we need to understand the particle density function. This is an empirical measurement, right? And then we have a prediction of Hard scattering, and we also need to understand the underlying event. So the plot I showed you in the previous slide, they are the compressed information by all of this altogether. Okay, so the PDF basically. What happens is that we use some low energy or physicality experiment to derive the particle distribution function. So it's the structure of the protons. And we believe it's a universal property. So we can try to project it to the higher momentum transfer process like a Large Hadron Collider. And that's how we do the include PDF to this calculation. If you look at the uncertainty for the PDF, you can see that the Coulomb luminosity uncertainty, they have quite high uncertainty in the very low x or very high x. Okay, so here this is the range that if in Large Hadron Collider we have opportunity by doing the Large Hadron Collider measurement to as a feedback to this range. For example, this is the first attempt of using the top cross-section measurement in Large Hadron Collider and combined with the PDF data. And this is the first fit we have. You could see that the green one was the original PDF without the Large Hadron Collider data. And the rate is the inclusion of the Large Hadron Collider data. You start squeezing the uncertainty. And also, the old data actually compared to the most up-to-date data, you can see that we start seeing that the necessary of correction of Coulomb PDF. And this is a very nice result that how the CERN measurement in Large Hadron Collider can start contributing to the PDF. Okay. And then I would like to talk about QCD. Basically, major things that we want to understand how all those interaction that produce the Coulomb object, how we can understand it well in the Large Hadron Collider. So, for example, we can calculate the differential transverse momentum distribution of inclusive jet production. And you could calculate the living order production, and also theory try to move on to apply higher order correction to these calculations. Then we can compare to our experimental data. And this shows one comparison that you make some threshold cut on the jet T and just count the number of jets. And you can compare the black dot is the data, and then compare to the theory predictions. Yeah. So this so far that we can see that the agreement between Data Monte Carlo quite nice. Once we increase more luminosity and also increase more energy, so we can start probing to the even extremely higher multiplicity if we have an agreement between the Data Monte Carlo. So why this is important? Because in some of the Beyond Standard Model scenario, you could predict a very high multiplicity of the jet, and understanding of the Standard Model is the key to verify if we have a new physics. So for QCD, you can also understand the strong coupling constant. What the LHC can do is that if we just look at a single measurement of the alpha S, the uncertainty actually could not really compare to what the world average is. However, what is unique for LHC is that we can do the alpha S running coupling to a very high Q that is unique that low energy physics cannot do. Yeah. So as we go to the even higher energy collider, then we start probing the extreme area of the Standard Model. For example, the high transport moment jets. Okay, so this is an example that we can measure the jet mass of the inclusive jet production, and this is an example of one transverse movement being between the 300 and 400 GeV. And you could see that the break, the data, the rate Pythian is the leading order generator that's quite popular used in large hadron collider. So you can see that it cannot, it has quite some discrepancy from the real data. And Hurwitz is a different parton shower generators that we have quite also use popular in hadron collider physics. And in this scenario, it have relative also not quite good description of the data. It push a little bit the other side in the high side. So this is a ratio comparison of two. So this is one of the things like we would like to push more. Is this discrepancy coming from the less understanding of the parton shower model, or if this is actually some real physics coming in? And this is a question that unless we can fully understand how those parton shower work, that we cannot set a conclusion. Yeah. So yes.
That is single divergence.
This right. This is high energy. Right. This should be. This is a Dirichlet event. Right. With early data. Yes.
But this is the similar
Actually, I should check what's the latest result. Yeah. Okay. I knew that we have worked on that, but I'm not sure that what's the latest data set we can have in terms of publication.
very early.
This is very early, right?
A picoball.
Right.
I think it will be difficult. It's
But
higher is serious.
the nice thing is that this has a low pile up. That's why I choose that. Yeah. Yeah. Okay, so I would like to do a little bit more on this subject. So the QCD, this is a cartoon show that you have production in the collision point, then you have a charge track with the trajectory in the tracker, and you have a calorimeter cell in the calorimeter. So the typical scale when you produce the quark or gluon, they are usually in 100 GeV or even to a TeV scale, how the scattering. But through this showing process, in the end, the final stage of jet structure is solved. They are non-productive QCD. Okay? So the formation of hadrons from gluons, and they are in the order of about 100 MeV energy scales. Okay? But when I say this, actually, sorry, I put the wording a little bit misleading. I'm talking about all of these happening right here. So they're the QCD scale. Then they just fly, then showering in the calorimeter. So because of this scale, actually, this structure of the jet, it could be analyzed perspectively. So this enables the precision QCD calculation, and we can compare to the measurement in LHC. And the other thing is that the ELU scale actually is W boson, Z boson, Higgs boson. They are around the 100 GeV scale. So they are also within this calculation scale. Okay? So this is more for the expert who knew about the jet clustering. But just make it similar. Remember that in a calorimeter, you have energy deposition of multiple cells, right? So how can we cluster all different constitutions? Say that this group belonging to the same gluon quark, they deposit energy here. So we develop an algorithm that trying to we start from a seeding, like we can compare all the energy cell. We identify the one which have the highest energy with respect to the noise of the cell. Then we start from here as a seed. Then we try to find the neighboring cell which have the energy beyond the 2 sigma of the noise. And then we connect them together until the point that the energy is less than the energy cell. So then we stop. Then we stop here. So here will be the adjacent. We call it the clustering process. Then you start from uncorrelated constitution. In the end, you are growing, and make a connection over different constitution. Then you get the final jet cluster. Okay. So if we have to pick any cell, they are connected some way. Then we use some naive way that just find the equal distance of the two peak of cluster. Then we split into the two. Okay. So as I mentioned earlier, that the jet it should not just come from the quark and gluon, which is a QC process. And if you have an electric object like W, which decay to UD bar, and or top quark decay to W boson plus B jet, W also decay hadronically. You have a 3 quark in the final state. So those are so-called color singlet object, which is those quark actually they come from some carrier particle which is no color. Okay, but if in the high energy environment like a hadron collider, if this particle have a really high transverse momentum, then we have a case that these particles they will be boosted into a very small area, and they could be just reconstructed as a single jet object. All right. So in this case, the splitting I mentioned earlier become critical because if you have a jet, then you find that they have 2 local maxima, and you can split them to the 2 subject. Then you have a chance, you have a way to control. This might not be background, but real color singlet object. Okay. So this is actually a field we call the jet substructure field. That how we can discriminate this object from QC object. Everything is nice as I did so far, except if you look at real event. Real event look like this. You have a lot of pion